Yeah, so let's begin today with the discussion of the quiz that we had last week. I'll go through the answers quickly so you can check against your answer books. We start with question 1, which was just true or false, and the first statement was a conservative dynamical system given by an equation of motion of the form x dot is f of x, x dot is f of x, and we are told it's conservative, cannot have any attractors. And the answer is that it is true, because for a conservative system this implies that del dot f is equal to 0, and if that is so, then we know that the volume element in phase space is preserved under the flow. So since we have defined a conservative system as one in which the volume elements do not change under the flow, a conservative dynamical system cannot have any attractors, because if you have an attractor, no matter what the nature of the attractor, either a point attractor like a critical point, or a limit cycle, a stable limit cycle, or more complicated attractors, the fact is that all the points in the basin of attraction of this attractor would eventually asymptotically fall into the attractor, and therefore there is definite reduction in phase space volume. And since a conservative system, the flow does not allow for any change in the phase space volume, it cannot have any attractors. Hamiltonian systems of course are special cases of conservative systems, and they would not have any attractors either. The next question asked, the harmonic oscillator is the only system whose time period of oscillation is independent of the amplitude of oscillation, and this is false. We have ourselves seen a number of oscillators, isochronous oscillators, whose time periods are actually independent of the amplitude of oscillation. These are called isochronous oscillators because it means that the amplitude, the time period of oscillation is independent of the energy of the oscillator. Under special circumstances this can happen even in a nonlinear problem. Yes? I stated that a basic characteristic of the linear harmonic oscillator is that it is isochronous, that it does not have a time period which is dependent on the amplitude or the energy. But the converse is not necessarily true, that if you have isochronicity, it does not necessarily imply that you have a harmonic oscillator. You could have nonlinear oscillators which would do the same thing. Here is an example of an oscillator whose time period would actually be independent of the energy of the oscillator. Consider for instance motion in one dimension with a Hamiltonian given by p squared over 2m plus 1/2 m, let us call it k x squared, plus a force which goes like a, some constant a, over 2 x squared, potential of this kind. Now what would the force on this particle be? It would be minus the derivative of the potential, so the force on the particle is minus dV over dx, this is equal to minus kx, that is the harmonic oscillator part, and then the derivative of this potential which would go like plus over x cubed. And what does this do as x goes to 0? What does the potential look like in this case? What is the shape of the potential? So let us plot V of x is equal to 1/2 kx squared plus a over 2 x squared, where k and a are positive constants. And then if I plot this potential, here is x versus V of x, it clearly goes to infinity as x goes to 0 on both sides. It also goes to infinity as x goes to plus or minus infinity, and of course it is clear that in between it comes down and does this, and symmetrically so on this side as well. And the particle can oscillate either in this well here or in this well here quite symmetrically. For the same energy it could either have a center of oscillation on the left hand side or on the right hand side, and if you compute the time period of oscillation in this potential, it turns out that it is actually independent of where you are, of what the energy is. I leave that to you as an exercise to check out that this oscillator is isochronous, and it is not a linear harmonic oscillator because the force is not just proportional to the negative displacement but also has an extra term here.
What is the definition of harmonic?
When I say linear harmonic or harmonic, I mean that the potential is a quadratic function of the displacement, and that is all that is needed. Anything beyond that is nonlinear, and the reason it is nonlinear is because the equation of motion becomes nonlinear. Recall that the equation of motion here is x dot is delta h over delta p, so it is p over m, but p dot is minus delta h over delta x, and that is minus kx if you restricted yourself to just this. But if you also included the nonlinear term, you have an a over x cubed. So this is the reason why we call these oscillators nonlinear, because the equation of motion is no longer linear, it has nonlinear terms in the coordinates.
So,
yeah.
what is the difference between linear harmonic oscillator and general harmonic oscillator?
Now the reason I kept saying linear harmonic oscillator, which you are used to calling as a simple harmonic oscillator, because we also looked at the word linear there was a bit of a misnomer. I should have said one dimensional harmonic oscillator because the oscillation was in one direction, the x direction alone. We also looked at combinations of oscillators, oscillator on a plane, oscillator in 3 dimensions and so on. They are not linear harmonic oscillators, they are just harmonic oscillators. So I use the word linear in the other sense, namely along a line, motion along a line, a given line. Should perhaps not do that, should just call it a one dimensional harmonic oscillator in that case. But every harmonic oscillator has a linear equation of motion, linear in the coordinates and momenta, and when you introduce nonlinearity in the potential, you at once have these extra terms, and it is not at all guaranteed that the oscillations would have a time period independent of the energy, but in this particular case it turns out that they do, and that is an interesting exercise to look at. There are profound implications to this. This model here is not pulled out of the hat, it has further implications, and it is a specific, it is a member of a specific family of potentials, a model which has many other interesting properties. So even though the potential does not look parabolic at all, the oscillations in this are independent of the energy of the oscillator. This could very well happen. We saw, however, that if you took a potential of the form a power of x here in one dimension, just a power of x, no extra terms, then the only oscillator which had a time period independent of the amplitude was in fact the harmonic oscillator, the quadratic power here, nothing else. But that was restricted to the class of potentials which just had a single power of x and nothing more than that. More complicated functions could do this. There are in fact an infinite number of potentials which would lead to oscillations independent of the amplitude of oscillation or the energy in general. Okay, the next question.
Is there anything which characterizes the form of, is there any, those which are reciprocal, is there something which characterizes their functions?
In what sense? The question is there anything which characterizes the potentials?
Okay, this is the class of, this is the family of functions which are isochronous and nothing else.
Not so simple to classify, not so simple, it is possible to a certain extent but not so simple. These models, the one with the x squared and the 1 over x squared, they are part of a much bigger family of potentials where this property would be satisfied, not just in one dimension but in higher dimensions as well, or not just with one oscillator but many oscillators on a line. It's not a, this is not a sufficiency condition, this is not the only one that does it, in the sense that it's not a unique property to this particular oscillator. There are other potentials, many other potentials which would do this, and to some extent they can be classified. We will not get into that right now. Okay. The third question was straightforward. It said, consider a canonical transformation of an autonomous Hamiltonian system. Under such a transformation, the form of Hamilton's equations is preserved, although the functional form of the Hamiltonian in the new variables need not remain the same as the original one. That in fact is what happens in a general canonical transformation, so the statement is quite true. The next one says, every dynamical system given by an equation of the form x dot equal to f of x can be transformed into a gradient system by a suitable choice of dynamical variables. So the proposition is that this could always be transformed by a suitable choice of variables to look like y dot is equal to the gradient with respect to y of phi of y. No such guarantee at all, because this would imply that every vector field could be writable as the gradient of some kind of scalar. This is not certainly true, it is certainly not true at all. So it is not necessary that this should happen. It is not true that every dynamical system can be transformed to a gradient system by suitable choice of variables, change of variables. We go on to the next. Homoclinic orbits can occur in both conservative and dissipative systems, and the answer is yes, indeed they can, because all that a homoclinic orbit does is to start at a saddle point, part of its unstable manifold goes out and comes back, forms a loop eventually, and the part that comes back is part of the stable manifold of the saddle point, and there is no restriction on this. It could happen in a dissipative system, it could happen in a conservative system as well. Pardon me? It does not matter whether the volume elements change or not, because you are only talking about a single trajectory here, and there is no reason at all why this cannot happen, independent of what else happens anywhere else. Okay. Linear stability analysis need not reveal the correct nature of the flow in the vicinity of a critical point that has a center manifold. This is the whole point about center manifolds, and it is certainly a true statement. It could, but on the other hand it might let you down, and therefore you have to go beyond linear stability analysis, as we saw with specific examples, once you have a center manifold. The Liouville-Arnold criterion for integrability is applicable to any even dimensional dynamical system, and that is false, because the Liouville-Arnold criterion is specific to Hamiltonian systems, which form a special class of dynamical systems of even dimensionality. So there are many other systems, innumerable systems, which have nothing to do with Hamiltonian systems, and there is no question of anything like this criterion in those cases. The next statement said, a bifurcation occurs at some value of a parameter in a dynamical system if the nature of the flow changes qualitatively as the parameter crosses that value, and yes indeed, that is the very definition that we have used for elementary bifurcations. The critical points corresponding to an undamped simple pendulum can only be centers or saddle points. That is also true, because this is a Hamiltonian system, undamped simple pendulum, therefore there is no attractor in the problem. It is a Hamiltonian system, and the only critical points you could have in this simple system are centers or saddle points, and we saw that you had centers and saddle points alternating, corresponding to the minima and the maxima of the cosine potential. Consider a two-dimensional dynamical system given by the following equations: x dot is x squared minus y squared, and y dot is equal to 2xy, and the proposition was the critical point at the origin is a saddle point, and that is false, because the saddle point, a saddle point has a winding number. The vector field corresponding to a saddle point has a winding number of -1, but this is a dipole field and the winding number here is 2, and this is topologically quite distinct from a saddle point, and it is a higher order critical point, because this is not even linearizable in the vicinity of the origin. There are no linear terms here at all, it is intrinsically nonlinear, and it has happened by the coalescence of two singularities, two simple critical points.
When you say a critical
Yeah.
point at
Yes.
the origin,
Yes.
does it imply that one of the in the unfolding one of the critical points is a saddle point, or as a whole it is a saddle point?
It's not, no, it's a critical point. I mean, that's it. So there's no question of any unfolding or anything like that. This is just a critical point as it stands.
If an unfolding
Yes.
gives rise to a saddle point,
It could, like a saddle node, for example. It could. It could. Yes. But I won't call.
would the statement be true then?
No, I wouldn't call it the saddle point at all, because this is the statement being made has to do with the singularity of this vector field at the origin. So it's a local statement about the singularity at the origin, and that is in this case undoubtedly a dipole singularity, and therefore has a winding number 2, and it is not a saddle point. It cannot be deformed smoothly into a saddle point, because the winding number is a topological invariant, and it says that no matter how you transform coordinates and shift and bend and so on, you can't change the nature of you can't change the winding number. So a saddle point remains a saddle point. On the other hand, that wasn't true for nodes. You saw, for instance, that something that looks like a source, a radial field, could become a tangential field. So something that looks like a node could transform into a spiral point and so on. These could be done by smooth distortions, but certainly you can't take a saddle point and convert it and distort it into a dipole field or anything like that. So a Hopf bifurcation can only occur in a dissipative system, and it is true because a Hopf bifurcation is one where a limit cycle is involved, and it is a bifurcation where a stable critical point bifurcates into a stable limit cycle and an unstable critical point, or if it is a subcritical bifurcation, an unstable critical point bifurcates into an unstable limit cycle and a stable critical point. In either case attractors are involved, and therefore this sort of thing cannot happen in a Hamiltonian system, or more generally in a conservative system, but it can certainly and does frequently happen in dissipative systems. Finally, if the Poisson bracket of A with B vanishes and that of B with C vanishes, then the Poisson bracket of A with C necessarily vanishes. Now that is false, because all you can say from the Jacobi identity is if A with B is 0 and B with C is 0, this would imply then, and you are asked to find out if the Poisson bracket of A with C vanishes, what you can say, assert, is that the Poisson bracket of this is 0 by the Jacobi identity, because the other two terms drop out, and all you can say is that this quantity needn't be 0, it is some function whose Poisson bracket with B happens to be 0, and that is about it. So you can't say anything more. However, if you have 1 degree of freedom systems and they are Hamiltonian systems, for example a single 1 degree of freedom Hamiltonian system, and then you know that the Hamiltonian in an autonomous case is the only functionally independent constant of the motion in the problem, then anything else which you find which is also a constant of the motion would necessarily have to be a function of the Hamiltonian. And then of course if A is the Hamiltonian, B and C are functions of the Hamiltonian, then of course all the Poisson brackets of these quantities with the Hamiltonian vanish, but that is not true in general. In general this is all that you can assert. Okay. Now we had an implication to this. The implication was that in a Hamiltonian system, if you set B equal to the Hamiltonian for instance, then A with B equal to 0 implies that A is a constant of the motion. Similarly C with the Hamiltonian equal to 0 implies that C is a constant of the motion, and then this statement implies that the commutator, the Poisson commutator of A with C, the Poisson bracket of A with C is also a constant of the motion. So what it implies is that in a Hamiltonian system, if you find two constants of the motion, their Poisson bracket, if it is not trivial, is also a constant of the motion. So it has a practical use in that instance. The next question was multiple choice. You considered a general Hamiltonian system, and the first statement was the Hamiltonian is always a sum of a kinetic energy term and a potential energy term which depends only on the generalized coordinates. This needn't be so at all, because I pointed out early on that all that a Hamiltonian system needs is that you have an even dimensional phase space with a certain structure, the Poisson bracket structure, canonical Poisson bracket structure, and a Hamiltonian function specified to you which then determines the equations of motion of all the variables. There is no restriction that the Hamiltonian should be of the form of a kinetic energy plus a potential energy. That is only true for simple mechanical systems, not true in general. In fact, even the statement I made about a Hamiltonian system, namely that it should be even dimensional and it should have this canonical Poisson bracket structure, could be generalized. There are more general forms of writing Hamiltonian systems where you do not even need to have an even dimensionality of the space, where the meaning of the Poisson bracket itself could be generalized further, but that is the mathematical detail we have not got into, but certainly does not have to be a sum of a potential and a kinetic energy. Saddle node bifurcations cannot occur in this system. They certainly can. Saddle node bifurcations, we saw with an example of a potential itself that a saddle node bifurcation certainly can occur in a simple potential problem, Hamiltonian problem. The dynamical symmetry group of transformations need not necessarily be identical to the group of canonical transformations, and that is certainly true, because the dynamical symmetry group of a Hamiltonian system could be much smaller than the group of canonical transformations. If you recall, in n degrees of freedom, the group of canonical transformations was the symplectic group 2n over the reals, whereas the dynamical symmetry group would depend on whether the Hamiltonian had some special symmetries or not. and most Hamiltonians do not, and when they do they have much smaller symmetry groups. The example we took was the 2-dimensional harmonic oscillator, which had a symmetry group whose canonical group of canonical transformations was the symplectic group 4, sp4 on the reals. On the other hand, the symmetry group of the Hamiltonian itself was the group of rotations in 4 dimensions, SO4, and the intersection of these two was a much smaller group which was isomorphic to SU2. So we saw that this need not be true at all. Action angle variables necessarily exist for the system. Again, no, because the Hamiltonian need not be integrable completely at all. In fact, you could have a few action variables less than n in number, and that is not sufficient to integrate the system completely. So they need not exist at all in this sense. Remember that once an action angle pair exists, then the angle variable does not appear in the Hamiltonian and it becomes a cyclic coordinate, and this is not always possible in general. If it is fully integrable, then the statement is, under suitable conditions you have an action angle transformation which will then lead you to a set of variables in which all the angle variables disappear from the Hamiltonian and the Hamiltonian is a function of the action variables alone, which are then constants of the motion, but that need not be true in general. The next statement pertained to a general autonomous dynamical system described by a set of n coupled nonlinear first order ordinary differential equations like x dot equal to f of x. The phase space can be either even dimensional or odd dimensional, and that is certainly true automatically. There is always at least one attractor in the system, not necessary. For instance, if it is a conservative system there would need be any attractors at all. The dynamics is necessarily measure preserving, not at all. It could be a dissipative system, so it could very well have a measure which shrinks. There must exist at least n functionally independent constants of the motion that do not have any explicit time dependence. No, because if that happens you can't have any motion at all in an n dimensional space. So if you have n constants of the motion which are independent and do not depend on time at all, then the system can't even be integrated. There is no motion, there is absolutely nothing to do. Once you have specified the initial conditions, the system just remains there, you can't move out after that. So that is not valid either. Okay. We go on to question 2, which was fairly straightforward. And the system was specified in polar coordinates by sine pi over r and theta dot equal to r. In plane polar coordinates we are asked to find, in this case, the limit cycles of the system, if any, as well as the stability. And it is immediately clear from here that limit cycles at r equal to 1 over n, where n equal to 1, 2, 3, etc. exist. And then this becomes sine pi and it vanishes, so r does not change on those points and you get circular limit cycles. So you get a family of concentric limit cycles of radius 1, a half, a third, and so on and so forth. Now if I took the system near one of these limit cycles, in the vicinity of one of these limit cycles, then r dot is approximately equal to sine pi n, which is 0, plus r minus 1 over n. The derivative of this at r equal to 1 over n. The derivative of this is of course pi times cos pi over r, but r is 1 over n, so this becomes cos pi n times the derivative of this, which is minus 1 over r squared, which becomes minus n squared, plus higher orders. So this becomes equal to minus pi n squared minus 1 to the power n r minus 1 over n, plus higher order terms. And if n is equal to 1, this gives you a minus sign along with this, and then it says r dot is proportional to r minus 1 with a positive coefficient here. Therefore for sufficiently large values of r, this flows out because r dot is positive, it goes away, and if r is less than 1, it flows away inwards. And so it is clear immediately that at r equal to 1, this particular limit cycle, this limit cycle here, whatever is inside here flows out, whatever starts here flows out, because theta dot is r, If r is greater than 1, theta dot is a positive number and it increases, and therefore you expect it flows off in this fashion. And since theta dot is positive, the flow is in the counterclockwise direction on this limit cycle, and anything which starts in is going to flow away from it towards the next limit cycle, which is the limit cycle at r is equal to a half. So things flow in towards this, and similarly between 1/3 and half things flow out towards the half. So you have an infinite number of limit cycles nested within each other. The outermost one, r equal to 1, is unstable, the next one is stable, the one inside is unstable, and so on all the way. So that is a full phase portrait. What happens at r equal to 0 in this case? What can you say about r equal to 0? Well, this function does not have a limit as r goes to 0 here, that is quite clear, and what you have is an accumulation of limit cycles of alternating stability. So it is a crazy singular point, but it is just an accumulation point for limit cycles, and that is about all you can say as r goes to 0. So the flow gets more and more and more intricate as you get inwards towards this. It is not a simple critical point by any means. Okay. Well, it is like asking, as n tends to infinity, is it even or odd? I mean, right? So it is the same problem as before. The limit does not exist. The limit does not exist. So the whole point is that the limit as r goes to 0 of sin pi over r does not exist. There is no definite limit. That is it. In what sense? Well, it is clear that everything we write down here mathematically is modeling some physical system to some degree of accuracy. So the question of whether it actually is describing, does it actually describe a physical system right down to r equal to 0 is a moot point in that sense, very unlikely to happen. Right. Let us go on to the next topic, and I would like to introduce to you the idea of Lyapunov functions, Lyapunov's direct method, which I briefly mentioned a little earlier, and what I intend to do is to work out a little bit of this in terms of examples and maybe give some problems so that you could work out things and see how this method works. Now this method is useful, it is a method for analyzing the stability of a critical point, and it differs from the linearization method which we learnt about so far, where if you recall we took a particular critical point, we linearized the system about this critical point, and then if the eigenvalues of the Jacobian matrix at this point had no 0 real part and the point was hyperbolic, then we identified the stability or otherwise of this critical point based on what the real parts of these eigenvalues did. If all the real parts, if at least one real part is positive, you ended up with something that was unstable, some direction in which things would flow away, but if all of them were negative, things flowed in asymptotically and you had asymptotic stability. We also saw that if you have a center manifold, if there are eigenvalues whose real parts are 0, then either you have a center or you have more complicated behavior, but the stability is not uniquely decided by linearization about that point. In those cases, Lyapunov's direct method helps you to do this, and the method works as follows. Suppose for this dynamical system x dot equal to f of x, suppose you have a critical point at x equal to 0. So let us consider the origin to be a critical point without loss of generality and see what happens in the neighborhood of the origin. So here is the origin, and there is some neighborhood of the origin in which if I can find a function, and let us call it v of x, it is called a Lyapunov function with the following properties. V of x is such that v of 0 is equal to 0, so it vanishes at the origin at the critical point, and v of x is greater than 0 at all other points in this neighborhood. I then say v of x is a positive definite function. So if this is true, I say v is positive definite. On the other hand, if it is also possibly equal to 0 at one or more points in the neighbourhood other than the origin, then I say it is positive semi definite. And the similar statement is true for negative definite and negative semi definite. If it is less than 0 everywhere, then it is negative definite, less than or equal to 0 it is negative semi definite. Okay. Now V has nothing to do with the dynamical system, it is just a Lyapunov function, an auxiliary function which I am going to try to find. Then the statements are as follows, Lyapunov stability theorems, and there are many of them, but in their simplest form the stability statements are as follows. Statements are in brief: 1, if there exists a positive definite V and if V dot is less than 0 in the neighbourhood in which V is positive definite, by dot I mean the time derivative of this V, then the critical point is asymptotically stable. Two, a little less rigorous, a little less stringently, if there exists a positive definite V and if V dot is less than or equal to 0, could vanish at some points in the neighbourhood, then the critical point is stable. Recall again that a center was stable but not asymptotically stable. A spiral point, an asymptotically stable spiral point, definitely things fell into this spiral point but need not be stable. So these two do not exclude each other in some sense, they are independent concepts. And finally, yes, not necessarily, we will see examples. So things could be stable and asymptotically stable, but they could be asymptotically stable without being stable. Okay. So the statement has got to do with finding specific Lyapunov functions. Of course, as you can see, if I can find this, then definitely I assert that the critical point is asymptotically stable. But if I can only prove this, and there are points where it vanishes and I cannot prove that it is actually non-zero at every point, that V dot is less than or at some points equal to 0, then all you can say is that the critical point is stable.
There can be points where it is stable but not asymptotically stable.
We are going to see this with examples right away, yeah, what happens. And 3, you also have a statement of instability. If there exists once again positive definite V and V dot is greater than 0, then the CP is unstable. Many refinements of these statements are possible, but I am just giving the simplest version here and we are going to look at examples. Okay. Of course you could turn this around and instead of V you consider minus V, then of course if V is positive definite and V dot is greater than 0, it would translate into saying if V is negative definite and V dot is less than 0. So instead of V you could always choose minus V as your Lyapunov function, and then whatever you say about positive definiteness becomes a statement about negative definiteness. Now let us look at examples and see how to apply this, and I am going to go through a series of examples, but you will see how powerful this theorem is, but we need to know what V dot has to do with things, and the reason is, the explanation is very simple. If I consider V as a function of x and I consider dV over dt, which is V dot, what is this equal to? Well, it is a function of x and therefore this is equal to delta V over delta xi dot. But from the flow equations on the solution trajectories, this is also equal to delta V over delta xi Fi of x, the ith component of the vector field f, and this is summed over I, the summation over repeated indices is implied. I have not written it down, but this is I equal to 1 to n, and this is of course equal to grad V dot f. Now what is the direction of gradient of V? If V is a function, in what direction is gradient of V? It is normal to the level surfaces of V, and the flow specifies the direction in which the trajectory moves in phase space. So you can see that this quantity here is telling you something about the relative directions of the gradient of V and the direction of the flow. So it is like having a level surface and finding out if the flow is going inwards into this surface at all times, in which case it has to go and hit some point, or is it flowing out. So in very heuristic terms, that is the way in which the stability theorems emerge from a consideration of dV over dt. But let us look at an example right away. So fix ideas in our mind. Let us look at this simple 2-dimensional system. Oh, and it is not restricted to 2 dimensions at all. So this is true for an n-dimensional system, and that is what makes it interesting. But let us look at simple 2-dimensional examples. So the first example I am going to look at is x dot equal to y dot equal to minus x, which is of course the harmonic oscillator all over again in suitable units. And now what can you tell me about this? What should I choose to be the Lyapunov function? Here is where there are no simple guidelines available. What would one choose as the Lyapunov function in this instance? Well, a good choice would be, we know already that this is going to be a center at the origin, and we know that it is stable but not asymptotically stable. What would you choose as a Lyapunov function? I would like to choose something that is positive definite, something which vanishes at the origin and in the neighborhood of the origin does not go to 0. Well, I would like to choose something that has got a definite sign, so it must be at least quadratic. Pardon me? I could choose x squared plus y squared, so I certainly choose that. If I choose V of x comma y equal to 1/2 x squared plus y squared, which you recognize is the energy of this oscillator in suitable units. I have set the mass and the frequency equal to 1, then this function is positive definite in a neighborhood of the origin in the sense we have defined it to be. It vanishes at the origin and it is not 0 anywhere else in a neighborhood of the origin. So what is the gradient of V? Its components are just x and y as it stands. What do you get if you combined it with this? So what do you get from gradient of V dot f? This is the vector field f. So it says take this component multiplied with this, take this component multiplied with this, and add the two, and you get 0. Therefore we go back here and ask, which of these applies? We have a positive definite V, and we have V dot not less than 0 strictly, but equal to 0. So certainly this criterion applies, and we are guaranteed that this critical point is stable. Now of course, if you could find some other V, some other function altogether where this was valid, then the critical point would also have been proved to be asymptotically stable, and we know that is not the case in the harmonic oscillator. So it implies that you cannot find a positive definite function V such that V dot is 0, because if you did, then it would contradict what we already know about the harmonic oscillator. Okay. Pardon? No, it does not say that at all. Why should it say that? If all you can prove is that V dot is less than equal to 0, then all you have established is that the critical point is stable. Okay. Now it is quite
less than 0.
Yes.
Then it will imply that it is asymptotically stable as well as stable.
No, why do you say that? Why do you say that?
Why
do you say that? Okay, now I see the confusion. No, if you can show that V dot is strictly less than 0, not 0, then you have shown that it is asymptotically stable, and in such cases yes indeed you proved stability, but you proved a much stronger statement as well here, but you do not go the other way. As in this example, all I have succeeded in showing with this Lyapunov function is that V dot, which is grad V dot f, is 0, so it hits this case here. I am unable to show that it is less than 0. So the statement I am making is that had I been able to find a Lyapunov function which was positive definite and for which V dot was strictly negative, then I would have been led to the conclusion that this critical point is in fact asymptotically stable in addition to being stable.
You are saying that again, right? If it is going to be, it may not be that if it is asymptotically stable, it must be stable.
No, it needn't be, but the Lyapunov criterion is telling you, see it is a question of the choice of the Lyapunov function. So the same function does not satisfy this as well as that is quite clear. So let us go over this again. I guess and pull out of the top of my hat a certain Lyapunov function, and for this Lyapunov function I show that it is positive definite, that is trivial, and I see that V dot is strictly 0, and then I look down here and ask which of these applies, and it is this case that applies. I conclude that this critical point is stable. Okay. Now if I did not know anything more about this system, this is all I could conclude about it, and then I might wonder perhaps this critical point is not only stable but also asymptotically stable. I would like to examine if that is so. If so, I need to find another Lyapunov function, some other cleverer choice of function where I could actually establish this, and I am unable to do so. So the point about Lyapunov stability has to do with a clever choice of a Lyapunov function, and the remarkable statement is if you can find even one Lyapunov function which satisfies the conditions of this theorem, then you can conclude whatever the theorem states, okay. But that may not be the best, this is certainly true, but this is a statement about stability here, okay. So we have seen stability for this particular problem, the simple harmonic problem, the oscillator problem, but we also know this problem can be explicitly solved and it is not asymptotically stable, it is a Hamiltonian system here. So the conclusion would be that you can't find such a V no matter how hard you try, but you have to understand that this is not it is not that you can do this in all cases. You are trying to find out if in the absence of any information some statement can be made about stability, and that is all the Lyapunov function does. So let us see a few more examples, then we come back and answer some of these questions.
So suppose a system
yeah.
has an asymptotically stable critical point,
yes,
which is not stable.
yes,
Okay.
yes,
Does that mean that I can't find Lyapunov function?
yes, you will not be able to find a successful Lyapunov function which would then satisfy this criterion as well, yes, yes indeed. Just as in this case we are not able to find a Lyapunov function, I am just asserting this so that this is so, that you cannot find a Lyapunov function for which this is true in this instance. No, it is not, I mean there are many extensions to this, but it is a starting point. So let us look at the next instance. The next instance we added something to the oscillator and we did the following. We put minus x times, if you recall, x squared plus y squared, but let us be general and let us put some phi of x comma y, and minus y phi of x comma y, where phi is a continuous function, it has continuous first partial derivatives and so on. What can one say now? I still choose this V, and then what do I get? I get gradient of V equal to x comma y, and therefore V dot is the gradient of V dotted with this, and what does that give you? So these two terms cancel, but I get a minus x squared phi, and then out here I get a minus y squared times phi, so this becomes minus r squared times phi of x comma y. Now the Lyapunov function I have chosen is certainly it's just the energy of the unperturbed simple harmonic oscillator. It is a positive definite function, vanishes at the origin, non-zero everywhere outside the origin, and I happen to choose this function and decide and see that V dot in this case is minus r squared phi. Now what can one say? Suppose phi is positive definite, then what would you say? If this is greater than 0, phi greater than 0 in a neighbourhood of the origin, it is positive definite, then V dot is negative definite, and therefore I would say the critical point is asymptotically stable. On the other hand, if I know that phi is less than 0, if that is the way this function is, then V dot becomes positive definite, V is positive definite, and I can certainly assert that the critical point is unstable, and this would apply. So without further analysis, depending on what this function does and the fact that I know such a Lyapunov function exists, I am able to make this statement about the stability of the critical point. So this is the power of Lyapunov's method, direct method. It is called Lyapunov's second method or direct method because it depends on your clever choice of these functions here. Let us, yeah.
Sir, but can't we choose x square plus y square?
Yes.
Lyapunov function everywhere.
The question is, can I choose, let us do the next example and see if we can choose x squared plus y squared as a universal Lyapunov function, see what happens. So the other problem, I do not want to erase this, the other problem we looked at was the simple pendulum, which too had linear harmonic oscillations for sufficiently small amplitudes. So let us look at that example and see what happens. And there we had x dot equal to y and y dot was equal to, on the right hand side, minus sin x for the undamped oscillator, and then if you put in damping you also had a minus y in this fashion. In suitable units, this was the damped simple harmonic oscillator with some special choice of units for the frequency and the damping coefficient. What happens now? And I am going to choose V as he suggested, I choose V equal to 1/2 x squared plus y squared. So this would imply that V dot is equal to x multiplied by this, so this is xy plus y multiplied by this, so this is minus y squared minus y sin x. I am interested in seeing what happens near the origin, near the critical point at the origin, where I know that there are going to be small oscillations if you did not have damping. I have included damping here. So what happens now? This becomes equal to y times x minus sin x minus y squared. And even if I say the neighbourhood that I am interested in is restricted to a small neighbourhood of the origin and y is approximately 0, so I neglect the quadratic term, as you can see immediately that x minus sin x could have either sign, and therefore you are finished. You cannot make a statement about whether it is positive definite or negative definite and so on, not able to do that in this case. So this is not a very good choice. What would you suggest then? This is not the energy of the simple pendulum at all, the undamped simple pendulum. So the next choice would be to say, shall I choose the energy of the simple pendulum itself, undamped simple pendulum? After all, that too is a positive definite function. Let us see if we can choose that as the Lyapunov function. So instead of this, I replace it with half y squared plus 1 minus cos x, which was the potential energy, and that is a positive definite function also, because the least value it has is 0 at the origin, and then there is a neighbourhood of the origin in which it has got only positive values. So what happens now? The gradient of V is equal to, I differentiate this with respect to x, and what do I get here? It is a vector with the following components, the derivative with respect to x, this gives you sin x and y. So this implies immediately that V dot is y sin x minus y sin x minus y squared, and this cancels out and you get V dot is minus y squared. What can you conclude now? This is the damped simple pendulum, remember it is the damped simple pendulum, and we are looking at what happens in the neighbourhood of the origin, but we already know what the origin is. What kind of critical point is the origin in the damped simple pendulum? It is definitely asymptotically stable. If it is an underdamped pendulum, it is a spiral point which falls in, an asymptotically stable spiral point. But what have we achieved here? We have got a Lyapunov function which is positive definite, we have got a v dot which is minus y squared, and what can you say about that? Can I apply the first one? Is v dot less than 0, or can I only apply the second one? This function, if it is negative definite, then certainly I can assert it is asymptotically stable, but unfortunately this vanishes not only at the origin but all along the x axis. So in a neighbourhood of the origin it vanishes everywhere here, and therefore it is negative semi definite, not negative definite. This is all one can assert, and therefore the conclusion is this critical point is stable. But we know it is stable and it is also asymptotically stable. We have proved its stability now, because the existence of this Lyapunov function guarantees that this critical point is at the very least stable, but it is also unstable, and that takes much harder work to do. It is not enough to do this, you need a much better Lyapunov function than this, and there exists one where you can actually show that this as a critical point is also asymptotically stable. So I hope this goes a little way in answering some of the questions that were raised, namely does this imply that, or does this imply this, and so on. As you can see, if you choose a bad Lyapunov function you can make no conclusions at all. You choose a reasonable Lyapunov function, you get some conclusions, but it could be even stronger, a stronger result could exist, but we have not been able to find it because we do not have a suitable choice of Lyapunov function. So the whole thing rests with finding a suitable Lyapunov function, trying to see if the best possible one is found in any given circumstance or not. What would happen here if I took an undamped oscillator but I wrote an equation of motion which was our generalized oscillator? I stop with that example today. So if I had x dot plus g of x equal to 0, there is no damping in this problem, and now I give you the following properties. This is 0, g of x is less than 0 for minus a less than x less than 0, greater than 0, 0 less than x less than plus a. So it is an undamped oscillator with some possibly nonlinear function of this kind. What can one say about this? What would you expect happens at the origin? What kind of critical point do you have at the origin? It is a center, you are completely right, it is a center, there is no damping, I expect some stable oscillations about the center. Therefore I expect to be able to find a Lyapunov function where I have this property here. Okay. What would you say is a suitable choice of Lyapunov function here? Yeah, the energy of the oscillator would be a good, the energy of this oscillator would be a good Lyapunov function. Now it is a Hamiltonian system in this case. What is the energy of this oscillator? This is the force here, this is like the momentum, y is like the momentum. So what would the energy be? I choose a Lyapunov function v of x comma y to be equal to 1/2 y squared, that is the kinetic energy, plus the potential energy which is the integral of the force with the change of sign. So this thing here is equal to integral 0 to x that is a positive definite function, as you can easily check with these properties, that is a positive definite function, and now you can write down what v dot does and find out whether it is stable or asymptotically stable, and a simple exercise shows you that the second of the criteria would apply, and this would indeed be a stable critical point at the origin. Okay. Let us try just one more example, and if I do not finish this we will look at it next time. X dot is equal to y and y dot equal to, let us look at the nonlinear oscillator, the cubic oscillator that we looked at earlier, the Duffing oscillator or a variant of it, minus x cube minus gamma y. So this is the friction term with a positive coefficient gamma. This corresponds to motion in a potential which has got an x squared part and an x4 part, and this is just the first statement that the velocity is x dot is the momentum on this side. What would be a good Lyapunov function in this case? The energy once again, so let us try that. So let us put v of x comma y equal to, we put a question mark to see if that is the best possible choice. So 1/2 y squared plus 1/2 x squared plus 1/4 x to the power 4, that corresponds to integrating this, the force here to give you the potential. This potential is just a quartic potential, it is not the double well potential of the Duffing oscillator. That would happen if I put a plus sign here, in which case you would get an inverted parabola near the origin and then a potential that goes like x4 up there, but it does not matter, you can give conclusions for both these potentials independent of what the sign you choose here is. So I leave you to figure out what happens in this case, what can you say about this potential, what can you say about this critical point. If you put it in, it is not very hard to see, all you have to do is to take the gradient of this v, compute it and multiply this and see what happens. So this implies that the gradient of v is equal to x plus x cubed, as you can see, the first component, and the other component is just y. So I have an xy, so this says v dot is equal to xy plus x cubed y, that is this times this, and then minus xy minus x cubed y minus gamma y squared. And of course everything cancels out, and what can we say about v dot now? Is it negative definite or is it negative semi definite? Negative semi definite. So once again we see that this is not good enough, all it says is that this critical point is stable, it does not yet establish if it is asymptotically stable or not. It is possible to find, and I will give you next time, a better Lyapunov function where you can actually establish that it is also asymptotically stable. Not surprisingly, it will involve gamma, you need to involve the constant gamma, and then you can show that you have a better Lyapunov exponent which will do the trick. Similarly, for the simple pendulum problem, choose the following Lyapunov exponent and show that the system is actually also asymptotically stable. For the damped simple pendulum, choose the Lyapunov exponent choose this Lyapunov function, and we can see that it is a positive definite function, vanishes only at the origin in its neighborhood, and then show that you indeed get v dot which is negative semi definite, negative definite, and therefore the critical point is indeed an asymptotically stable critical point. Okay. So let me stop here today and then we take